Yeah, so this is a user story, a bit like Roger's this morning. It's a case study of how R has basically enabled me to focus on my research, end up serving as an expert witness in courts in the UK, and also end up with a piece of software that's recognized in forensic science. It outperforms the other pieces of software that are designed by multiple software engineers, and I've done this single-handedly. And this is hugely, hugely hard to being able to build on various other pieces of software and put it all together in R. So this is my story. Okay, let's just go back a little bit. This is a street in Newcastle back in 2015 where there was a shooting. So imagine this red carpet. It was full of people a little while ago. It was a Saturday evening in June. And a guy on a motorbike, he drove past and shot at the bouncer. He didn't die, but this became a huge case, mainly because the day before, this bouncer had kicked out a young man from the nightclub, and that young man happened to be the local gangster boss's son. So this was thought of as maybe some sort of punishment for that action. So what happened was that in this case, there was a single piece of evidence that was a bullet with some wadding inside, and on that wadding was a piece of evidence, DNA evidence, and many people had touched this, so there was DNA from at least 5 people. And this is where I entered the picture because my friends in the UK, they couldn't actually handle 5-person mixtures, they could at most do 4-person mixtures. So, 3 years later, so fall of 2018, the Newcastle newspaper reported that actually the DNA evidence was overwhelming in this case. And I was really happy to see this because that was basically my work. It's like, this is my claim to fame. So, I'll tell you what the task is in forensic DNA analysis and why there was something for me to do. No, by no means the only person looking at these kind of things. So, a DNA profile is quite simple. You look at 16 well-defined places of the DNA. So, the idea is that we can identify a person through his entire DNA, but it's also enough, actually, to look at just 16 places where we know also what types of sequences we can find. So you will have something, 16 pieces looking, say 16 little graphs looking like this when you get the data from maybe a mouth swab of one person. You can imagine that a person has 2 bars to place for each marker. You can have either 2 different sequences at one marker, or you can have 2 of the same sequence at this particular marker. So if you take a swab from a person, you get the opposite problem. You have a graph, and you look, you simply just read off the profile. Where are there peaks? If there's a tall peak, you say, okay, this person has twice that particular sequence. If there are 2 peaks, these are the sequences. So that's very easy for a good piece of DNA. But for actual casework analysis, you don't get to see this. This you basically only get from swabs or really, really nice quality samples. In the real world, we mix DNA, and this could be, for instance, if I fight with someone, I happen to scrape them or whatever, there will be some DNA on me, like there will be DNA from me, and there will be DNA from the person that I fought with. So imagine there's some DNA, and there's a lot of DNA, maybe 70% from me, and then 30% of DNA from the person that I attacked. So now when you mix that DNA and you type it, you get this graph. You'll get to place 2 bars from me, where I have my sequences, and 2 other bars from the person that I've attacked. So in this case, we have no overlapping DNA sequences, but you could also imagine that one of the other markers, we happen to share a particular sequence. So then you will simply stack these bars. All right, so in practice, I actually have kind of the opposite problem, because I don't know the actual composition of this DNA. This is what the statistician is supposed to find out. So in practice, I get something like the graph in the middle here, and I need to work out how many people are there, how much did they contribute, sort of rework where to place these bars. So that's the quick idea. So why is this a difficult problem? Well, first of all, even if I knew this is two people with equally much DNA, okay, so I get to place two pairs of bars of the same height. Well, just in this simple figure, I can already place it in two different ways. So this is computationally not too intensive, but this explodes with the number of people that we add into this mixture. So it becomes a combinatorial problem. And also, I don't know what these mixture proportions are. Here I assume there was equally much DNA, but obviously I don't know in a particular case. And another problem is that these peak heights, they reflect how much DNA there is. That's why we had a person contributing 17% of the DNA had higher peaks, higher bars, and 30% had lower bars. But actually, these are not exact, they don't exactly reflect the amount of DNA. So there's also a statistical component in this. In practice, we know something about the variabilities that you will see in peaks if you know the actual DNA going into the mixture. So research-wise, I've been working kind of on two sides of this. There's the computational bit. How on earth can I kind of loop over all the possible ways of putting these particular bars? And statistically, how do I capture the actual heights of peaks? How do we use this in court? For this, I'll use a different example, which is a murder that happened in 2016, where I don't know, middle-aged man called Stephen Fredwell, he was battered to death. He lived in a ground floor apartment. He was quite unable to walk and get around his flat, and some three men entered his flat and simply kicked and battered him to death. There were some witnesses who saw three people enter and also heard the screams of torture. So, yeah, I have no idea why no one intervened. But long story short was that the police ended up finding three people that they thought could have done this. These are two of them that were convicted. And the guy on the right, he was wearing some gray jogging pants with a blood spatter on them. So this blood spatter was sent to an analysis, and it looked like the victim's blood or victim's DNA was somehow in this blood spatter. But again, there was a problem that this DNA sample was mixed. It's not too surprising because your trousers will generally brush against all sorts of things, and this kind of people also tend to share pieces of clothing used for various crimes. So it's very, very common that you will actually have a hugely mixed sample of DNA. So the police came to me, again, said we have this complex sample, we cannot, or our usual forensic science provider cannot handle it, it's too complex, can you help us? So their question to me was, is there DNA from this victim, Stephen Fredwell, in the blood spatter of Nathan Fenson's jogging bottoms? So to answer this question, there's a straightforward or a standardized way of doing it, which is something like this. It's not a yes-no question. You formulate two alternative hypotheses. One says something about, it's a reformulation of the police, the prosecution's suggestion, but it's rather specific. It's not, yes, his blood was in the sample. It is, this sample contains DNA from the victim, Stephen Fredwell, and 4 other people. that we don't know. We don't care about them. We just want to know that Stephen Fredwell's blood was there. And unknown individuals have a very particular statistical meaning. It means something like they are random UK Caucasian individuals that are unrelated. So there's a long statistical thing to unwrap there. But anyway, so the alternative hypothesis basically says, no, Stephen Fredwell's blood is not there. And they do that also in a very standardized way. They say, this DNA comes from 5 completely unknown individuals. Then what I do is enter my statistical model. I say, okay, so the first scenario is the prosecution's case, basically. And you can see the other one as the defense case. This is the alternative, the prosecution are not right. So I say, well, if the prosecution side is right, so if H1 is correct, how likely is it to see these particular data, this particular DNA sample? And I compare that to how likely it is to see the same data if the defense side is correct. So in essence, all the court really cares about is this likelihood ratio, saying how many times more likely is it to see data if the prosecution side is right than if the defense side is right. This is being interpreted in practice. So that's the one number I really need to report. So any piece of software should be able to compute that. And what happens in court, at least in the UK, is there's a layman jury, which will take this piece of evidence and many other pieces of evidence in the case into account. And they will try to sort of weigh for and against guilt. So if we zoom in just at when my piece of evidence enters, it goes something like this. The person will, judging in this case, will have formed an opinion of how likely is it that this is the victim's blood, or how likely it is that it isn't. So imagine they have 1-to-1 odds, so it's equally likely that it is and isn't his blood. Then enter my evidence, so more than 1 billion. This is what is overwhelming evidence, more than 1 billion. Well, what happens is that you multiply the likelihood of your data for the prosecution hypothesis with a factor 1 million. So what happens is the odds now shift. So these are essentially posterior odds. They shift to 1 billion to 1 for the hypothesis it's his blood. So now it's overwhelmingly evidence towards yes. But you could also imagine a situation where a jury member finds it more likely than not that it isn't his blood. So we say, okay, odds 1 to 20, that it isn't his blood. But then, because this evidence is so overwhelming, the weight scales will still tip towards this being his blood. So when you read in the newspapers that the evidence is overwhelming, this is basically what it means. It is that the LR, the likelihood ratio reported, was huge, and basically regardless of what your prior opinion of sort of guilt or not was, the scales are going to tip towards guilt. Unless you're extreme to the case of prior odds that are 1 to 1 billion. But if we have a case with many pieces of evidence, this happens kind of sequentially. This is what happens when seeing my piece of evidence, and then you could imagine tipping the scales again after seeing another piece of DNA evidence, and shoe prints and fingerprints and whatnot. And this is how someone like me enters the whole case. It starts off with the police being at some scene, collecting some DNA samples, and then they contact a forensic science provider, at least, so this is specifically to the UK. They contact a forensic science provider who will sort of analyze the DNA, and if possible, they will run a piece of software that gives the likelihood ratio. They will put that in a witness statement as the statistical evaluation, and then that goes to some defense experts who will read the witness statement and scrutinize it. In my cases, the forensic labs have always said we cannot actually handle this. So then I enter at the witness statement part, doing the statistical evaluations. The work, this little piece of work, is outsourced to me as an independent expert. So I would write a witness statement, which is a long document that says that I'm qualified to do this, which I'm a PhD from Oxford, so that helps a lot in the UK. So I'm qualified. The research behind my work, it's published, it's peer-reviewed in great journals. The software, is that good? So I've had to argue that this whole R package is actually reliable. So the software here it's called a software in the forensic science world, but we may also just think of it as it's just my personal R library. But, so is my whole computational reliable, meaning is R reliable? Is the external software that I also use and connect with that, is that reliable? My programming skills, are they reliable? So on. So it's a rather long document, and no one has contended it yet, so this is like huge victory also. Also for R, getting something accepted in court that was, like just an open source piece of software. All right, so I write something, the defense experts write something, possibly flaming at me, and we can either go to court and meet head to head if someone wants to see this. If they would rather avoid derailing the case completely by having someone like me rambling about statistics, what they will do is they will call a meeting of experts and sit us in a room. And this is a really weird experience, but you sit there and you decide on things that you can agree on and things you can definitely not agree on. And then you kind of write a joint statement that can be presented in court. Circumvented this whole sort of geeky thing. I mean, imagine layman jury. These are really just kind of random people from the street looking at lots of statistical experts flaming about should this software ever be used? I mean, this is just useless. All right, so oral evidence in court, that happens if necessary, but hasn't actually happened for me, and so it usually goes like this for me, and also the standard science providers is case is coming up, date is postponed, again and again. You are called to court, you are asked to buy your ticket, and the day before or a few days before you are said, well, we don't need you anyway. So you can kind of put your suit back in the cupboard. But okay, so why is this interesting for me? Where did R come into all of this? What did statistics have to contribute? So enter naturally in this whole workflow a range of sort of quality control questions that you might like to ask, especially when writing this witness statement, arguing the case that this number that you computed should actually be trusted by the jury. So my most useful example of this is the hypothesis that, so I was saying before, okay, the prosecution hypothesis explains the data 1 billion times better than the defense hypothesis. But that doesn't say that any of the two hypotheses were good at all. So then, of course, if you're comparing a crap hypothesis to an even worse one, your suspect shouldn't go to prison because of that. So that's like this usually convinces anyone that is good to do basically statistical model checking. Other things is we write this piece of software that can churn out a number, and it's based on lots of model assumptions, and these assumptions might not be right in general for DNA data, so we need to argue that this model is good. And we also need to check when we run this software on a particular case that the case data is not unusual compared to whatever we tested our system on. So either typing errors, because there's a lot of manual typing. You know, we get these little graphs with some heights on them. Some people have in the lab annotated this stuff. These numbers have to be copied into some sort of spreadsheet and then fed to expert software. So a huge process where stuff can go wrong. And that, all these kind of sanity checks is something that in statistics we've had this, well, for sure, a century-long tradition of checking systematically. So I always think of it as we claim something about data, and does it actually match what we see that data behaves? So I've been working a lot on making methods for doing these kind of sanity checks to see that, because basically any of these types of softwares, they will churn out a number and that will be presented in court, but there is no safety mechanism to flag when this is not a meaningful result. So that's kind of where I entered research-wise. And I wanted to introduce this kind of more statistical way of thinking about DNA evidence and how it was actually handled for court. And by that, I mean something like we have a well-specified model, as in I can write it down in a piece of, in a research paper, and someone else can read it and understand exactly what the model says. And there is some sort of inference, like you determine the parameters, for instance, whatever, maximum likelihood parameters. And you do your sanity check to see that the model you have then fitted to data also makes sense. And what I found is that R really encourage that sort of structure. Because if you think of how all the packages are constructed, like classical statistical models, it's something about a model object, then you can plot your data, you can fit the parameters, you can predict, you can plot the outcome of your model. So it's very, very modular and goes with the whole object-oriented type of thinking. And I was also already using R, and actually in thinking about what to say today, I realized just how much my statistical thinking is probably formed by R. So we were using R when I was here as an undergraduate, but I think particularly in, so I was 1 year in, I was many years in Oxford, but I came there in the applied statistics program, which was then led by Brian Ripley. So we were using the Mars book. So basically any new statistics we were doing, I was like, okay, model object in R, method to do something with this model in R. So there was this complete alignment with the structure of thinking and the way it was implemented. And it's been really, really, really useful for me to structure my way of thinking about this. So this is my little project, and this is a niche, like serious niche. There's, I don't know, very few people in the world doing this kind of thing. So it grew a methodology of these kind of samples. And I started structuring my thinking, realizing, okay, I'm doing the same little types of manipulations and there's messy scripts everywhere. So I simply bundling that into a package. So that already helped on actually shaping the research. And then it was also useful for sharing the research. And I've seen many other types of open source research projects. It's like, okay, we do this research, hey, we put it into a package and then other people can use it and we can kind of put the link in our paper. And you could say this is also a bit how it started. But then I realized, because my research was providing new methodology for the field, and also it was, so there's a huge amount of work on how to do these kind of things efficiently, that you will not see here at all. But I was claiming through my research that yes, we can handle more complex cases. We can address all of these questions that the end users have. It's just no one actually did it and provided the tools for it. So I was like, yeah, okay, here are the tools. So for me, it very much served like this sort of prototype software, a proof of concept. Like, it is actually possible to, be just me with my little crappy academic laptop and do a 5-person mixtures in a few hours, where these like big guys were with their big machines somewhere in a cloud, not being able to do more than 4. And then suddenly it was, maybe because I was actually able to run these cases, suddenly I was elevated to being, well, now you have a piece of software that is accepted for court, and it was recognized. So, it's actually pretty amazing when I was thinking about it. Because it literally just started with mess of scripts. So I was at Dirk's workshop yesterday, and he mentioned this. I forgot who he quoted, but like that everything is objects in R, and everything you do is apply a function to an object. Yeah. And then he also said very interestingly that built into R is this, or like an integral part of R is the ability to extend R with other software. And that is really, really, really something I've used. Because in my whole messy scripts was also that I had a piece of purpose-built software, which is called Hugin, which is basically a bundle of C functions that does a particular thing. It computes stuff on graphical models. So it's like highly specialized mathematical tool. It's not open source. It's good for relying on because you know exactly what goes on in it. It's simply a C implementation of a well-specified mathematical algorithm. So I was using that constantly, and then I realized that this previously postdoc in Oxford, he had written a whole API so that I could just import everything from Hugin into R, work with Hugin, never look at the horrible interface of Hugin, but just work with it directly from R and have my results in R, meaning that I could suddenly easily plot everything and do all the nice stats that I was able to do. All right. So this is, now it looks like a summary of the whole role of R. This is not the intention. But yeah, so one really main thing was the whole way of structuring, like formal statistical way of thinking that R really encourages. Then for both for research and for practical questions, I liked the extreme flexibility that you get when you implement everything as modularly as you do for R packages. Because if I want to change, for instance, the basic statistical model, then most of the methods for plotting and predicting, they're basically the same. So I can change just one little thing and get kind of a whole new piece of software. So there are many, many examples of where this flexibility really is a time saver. The other contenders, there are quite a few kind of these type of softwares on the market. Most are very closed source, as in hugely expensive. You have no idea what's implemented, so fine, I don't need to see the code, but please give me a paper that shows me what you have implemented. This is not the case, actually. The software that is probably currently being rolled out in Denmark has publications that I and other statisticians in my field cannot actually read and understand. This is like really, really scary, I find. This is the debate always in forensic circles always ends up on, should it be open source, not open source, and will we release the code? I don't want to see anyone's code. I mean, come on. I cannot meaningfully read it. I want to know what you set out to implement, and preferably also have someone justify that this is then what you actually implemented. And then, if you think of transparency in this, if I could at least just go and buy the piece of software and then test it, but first of all, not necessarily, well, I have that much money. We are talking hundreds of thousands of euros. But also, I had a colleague in the UK tell me that, well, he was trying to buy this piece of software, but they didn't want to sell it to him. They were simply afraid that he was going to reverse engineer it. Because we all do our little piece of software, and these guys are seriously afraid that we're going to steal their ideas. So closed source as in extremely non-transparent. So again, I didn't start out thinking I want to make an open source piece of software for this, but it has actually been one of the main kind of selling points or main novelties of this piece of software is that everything is documented for this particular software. Doesn't matter so much whether it's free or not. In my case, you will have to buy a license for this purpose-built software that's called Hugin. So it will still prohibit some people from downloading it and trying it, but it's still available, and it's especially available to the people who need to scrutinize it. You know, when a defense expert needs to read what I'm doing, they should also be able to check all of the details of my work. And this is actually not possible for the currently, well, most used real software. And then my final point is that R has helped me actually kind of move the entire field. Is again very much to what you talked about, Robert, that simply by saying, yes, this is possible, and here are the tools to do it, then certainly people will also kind of require you to address these questions or require you to do these analyses, because you can't just keep ignoring them. Because if you think of the DNA evidence, if people cannot make a computation for 5-person mixtures, then if you have a DNA sample which is more than 4 people, someone will look at it and say, oh, we cannot evaluate this piece of evidence, and it simply gets ignored. It's not part of the case anymore. So even just being able to go to 5 means that in these few cases, well, certainly there was a case because we could actually use the evidence. And you cannot just say, oh, well, I don't know if my model fits. I would say, well, then kind of show me that it fits. So it's kind of my take-home message slide. So what I've found myself able to do through this R package is that I've demonstrated that we can handle more complex cases. It is possible to evaluate 5-person mixtures, also using this peak height information, these more sophisticated models. And surprisingly enough, I mean, many people have actually been working on this and providing software, but for some strange reason, my software has actually been the first to get through cases, both in the UK and Denmark. I don't know exactly why. I'm still amazed about this, but also really proud. So it's always nice. And then this idea that you can also handle non-standard requests, that it's possible, for instance, to have, you take one DNA sample from one arm and one from my leg, and there might be some overlap in the DNA found here and DNA found here, because if I wrestle someone, their DNA is probably going to be in both. And therefore, you might want kind of a joint analysis. This is a very natural question from the police. Like, can you sort of, if you have a crappy sample from here and a crappy sample from here, can you kind of get more juice out of it if you make a joint analysis? And yes, you can. And we did this. And then the final, like, really cool thing is that by being able to provide all these model checking tools, especially visual tools through R, then we can increase the robustness of the analysis actually provided in court. Thank you.
It's kind of 3 questions, but it's more or less the same.
All right.
So the first one is, I'll give you all 3.
Yeah.
So the first one is if you can give an intuition why it's so much more difficult to go from 4 to 5. Second, how did they know that there was exactly 5 in the sample that you gave and not 6 or 7?
Yeah.
And can your software manage 6?
Okay, I'll start reverse order. My software can do 6. It can also do more if you have a bigger computer. But unless you have a really big one, I wouldn't push it beyond 6. And other nasty things happen because when you have 6, then you have more parameters to estimate, and then you have a bigger parameter space to search, which means that not only takes each computation of the likelihood function a long time, but you also need to evaluate it many more times. So it explodes computationally both in one evaluation and the number of evaluations. What was the other? It was...
Why it's so difficult to go from 4 to 5? Why is it specifically from 4 to 5 and not from 3 to 4 or from 5 to 6?
It's exponential, so it's everywhere. It just keeps growing exponentially.
It's just there. Okay.
Yeah, so the main reason is due to this, that you use these called random people, the unknown individuals, because you cannot rule out any profiles per se. You need to basically loop through all possible profiles for a person. And so if you, there are many possible profiles for a person, and then for each person you add, it just grows. No, there's no. It's just that if you take into account like the memory in my laptop, then there's like a breaking point at 5-ish. What was the second question?
How did you know there was 5 and not 6?
Yes, okay, so this is where I use statistics to argue, because you will not know. And if you can explain a sample with 5 people, you can also easily explain it by 6. Basically, imagine that we can always put in another person by just saying, oh, he has the same profile as I have. It's of course very unlikely, but it's possible. So usually you will want to start at the lowest number possible. Like how many people do you minimum need to explain this sample? There will be a number of peaks, so you need a certain minimum number. And then what I would do is say, well, if I go from whatever 4 to 5 people, do I see a significant increase in the likelihood of my data? It doesn't make sense to do like likelihood ratio type. You cannot do maximum likelihood on it because it will just keep increasing the likelihood. It's always better to explain a sample with more people. But there's like a practical limit. First of all, we cannot compute on 100 people, but also imagine what the jury wants to take into account, like how likely is it that there in the first place was 100 people's DNA on my trousers? So these considerations we also take into account. So we try to say, okay, let's do a simple hypothesis that we can kind of get away with, and that still explains the data adequately. But there is no great way of doing it. It's a heuristic way, however you do it. Yes? Say again, sorry, I cannot hear.
Is there a plan to switch to new technologies like next generation sequencing of DNA? Because you could get like millions of distinct copies of DNA from one sample, and then it's a good if the millions people mix like are.
Yes, there are some attempts of going to next generation sequencing. there are various issues. One is this. One is the precision of it. Like you can retype the same sequence many times, and then there's this thing called the coverage, basically saying how well are you reading this sequence, and that coverage has generally been very low, so the data was very noisy. So this is slow progress. I think there's also some issue with what's called reference databases. So there are these databases of profiles of people, for instance, giving me information of how common various profiles are in the data of genetic variants. And these databases are all with the old system. So changing to anything new will be like huge. It's not like it's easy to get DNA data in the first place, especially not databases.
Oh, okay, final question.
Yes, I have the reverse question. We'll
Yeah.
go back to yesterday's records. I mean, now you have 16 sites. I guess the computational problem would be easier with 8 sites, perhaps?
Not so much, because these sites are chosen basically so that they're independent, or very, very close to independent. So you can treat them independently, which means even computationally, you could just run everything in parallel.
Okay.
Yeah, so yes, it would be easier with 8, because then, but not really in practice. Yeah, exactly. I think we are.
Okay, let's thank